Now we start talking about the drag coefficients. So we define the drag coefficient as C sub D drag coefficient is equal to FD, which is the force of drag, divided by 1/2 rho V squared, that's inertial force effects, times A. And I said when I introduced this concept, this parameter, that A could be defined in various ways. It has three possible definitions. The most commonly used is frontal area. So for most relationships that you'll use this relationship in, A will be defined based on what's called the frontal area. And this is the area of the object as seen from the stream. That is the area that is the cross-sectional area normal to the stream of the object. So a sphere has a frontal area of pi r squared. That is, it has a frontal area of the circle that the stream would see if it were just looking at the stream, looking at the sphere if the stream had no depth perception. Since streams don't have eyes, we can certainly speculate that these streams that the eyes they don't perceive depth. So when they look at the sphere, they're just going to see a circle because that's what's in front of them, this circular object with a pi r naught squared area. If you look at a cylinder oriented parallel to the flow, so the flow is going to travel along the length of the cylinder, we see the same frontal area, that is pi r naught squared, because the only thing the stream is going to see is that face that's facing the flow. It doesn't see anything in the back, so it's just going to be, again, the same frontal area, that pi r naught squared. If you turn that cylinder, so it's a cylinder in what's called cross flow, so now the cylinder is oriented perpendicularly to the direction of flow, it's now going to see a rectangular object with area LD, where D is the diameter here of this cylinder, and L, of course, is the length of the cylinder. So the frontal area would be L times D. So that, as I say, that frontal area definition, that is the one that's going to be most often used when you're dealing with drag coefficient. So that should be your first instinct, is that it's probably going to be a frontal area. Another one that is used is called the planform area. Well, there are two others that are used, but in decreasing order of interest probably to people in this class. The planform area is area as viewed from above. So this is usually used for wings and hydrofoils. And one of the reasons for that, obviously, is that the frontal area of a wing is basically zero. So if you think of a sheet plate wing, kind of just the simplest of all possible bad wings, it's just a plate, might have a width of W here, and it has some kind of length of L, but its thickness is negligible. It's a sheet plate of metal. So you've got your flow coming in from this side, as we so often have looked at, flow over a flat plate, and you're seeing almost nothing in terms of depth of this plate. This plate could be very thin. So the planform area is often used for these kinds of objects that are thin and wide and long. And so this is the area viewed from above. So that's your planform area. So the planform area for this wing in this case would be LW, because that, for looking from the top of the wing, you would see that rectangular area above. The third type of area that is sometimes used, and it's used for ships, apparently. I've never actually done this, but is the wetted area. So that seems fairly self-explanatory. That would be the area that's actually wetted by, the liquid. I would assume it's obviously a liquid, that water in most cases, that this object is immersed in. So the wetted area is sometimes used for things, I guess, that are floating on top of water. I've not really seen that used, but I certainly accept the book's statement that it is. So used for ships and other floating objects. The final thing to point out is that you can break the drag coefficient into two components. There can be a drag component that comes from pressure. We know that for external flows, there often is stagnation pressure somewhere. So if you look at this sphere, this cylinder or sphere, and flow is coming in like this, there's going to be a high pressure spot there, and that's going to add some drag resistance to moving this object or moving the flow past the object. And then there are going to be frictional effects, of course, related to the viscous effects as the flow comes on by and causes shear stress along the walls. So these can be separated, but generally the relationship you get is not for the two separately. It's for the whole drag force that gives you CD. But it's good to be aware that the source of that drag can come from either pressure or viscous effects. Both are possible in these types of flows. Here are some just examples of drag coefficients. You find these in tables. Every fluid mechanics textbook has tables of these drag coefficients. You can find these drag coefficients, of course, on the web, tabulated for all different things. Again, there are lots of different ones. They're not necessarily in an agreement. There are lots of different correlations and experiments. So some of the standard ones are pretty well agreed upon at this point. If you're talking about cylinders and cross flow, so you have to imagine a cylinder that's infinitely long. So it's extending in and out of the paper, in a really, really long way. The length is much, much, much longer than the diameter of the cylinder. Then the laminar value for the CD is 1.2, and the turbulent value is 0.3. All of these are using frontal area. So as I said, you have to be very careful to know which area is being used in order to calculate the force from the CD. All of these relationships that I'm showing you here are using frontal area. So for a cylinder, we already went over this one, that would be the length of the cylinder times D. If you were trying to find that one. This next cylinder is also a cylinder. So again, very, very long in and out of the page. It's called a 2-to-1 cylinder, which means its diameter is D in this direction, and then it's twice as long in this elliptical longer direction. So it's kind of a narrower, flatter object, and so its drag coefficient goes down. I mean, it's shaped a little more like a wing, has a little better aerodynamics, or through the air. If the flow again is coming from this side, of course it would be worse if it were going the other way. So you get 0.6 there and 0.2 there. So that's your cylinder and cross flow there. If you have a half tube, you don't have a laminar value, only have the turbulent values here. But a half tube in cross flow here, again, you have to assume it's very long in and out of the page here. That gives you 1.2. And if you have a plate faced the wrong way, that is, if you have a plate that's really obstructing the flow, and it's long in and out of the page, it's skinny in the direction of flow, going out of the page, has some height here. That gives you a turbulent CD of 2.0. So all of these, these are just one of countless examples. You can find almost any shape you can think of has relationships for this. People have been doing these experiments for 100 years. They're really simple experiments to do. You just throw an object into a stream of air or stream of water and start measuring forces. So not a very hard experiment. So people were happy to do them. And there are lots and lots of relationships. So if you go on the web or go to one of those textbooks that's available to you, you'll see lots of charts of lots of these. Just make sure you pay attention to which area they're using. So it should say on the chart which type of area they're using, and make sure, of course, that the orientations are correct. If these objects aren't really, really long in and out of the page, that changes it. So if you have a sort of a short cylinder, that's going to change this drag coefficient. Again, you can find relationships that allow you to correct for the length of the cylinders or the fact that there is specific length if you look up these many, many relationships that exist.